Hey everyone, we are going to use derivatives to solve some genuine fake real life examples. So namely, we will use the idea of a min or a max to optimize some situation. So the way this works is we'll make a sketch and label variables. We'll write an equation for what you're trying to maximize or minimize. We'll get the equation in terms of one variable and specify a domain. That part's actually oddly important. And then we'll find the min or a max by finding where the derivative is 0 or infinite. We also have to check endpoints because those could actually do better than the true min or max, like depending on what the situation is. And then prove you have a min or a max by using the second derivative test. That's when it's, comparing it to when the derivative is 0. And then verifying the answer by graphing. And like related rates, we'll answer the question in words. So suppose you are building a catio for your cat Houdini. Catio is an awesome place for your cat to be able to go safely outside. Of course, everybody knows that. You're planning to use one wall of the house as the side of the catio. So like that blue line is the wall of the house. And you have plenty of building materials, but you need to put a line around on the ground. It's basically like your foundation. And for that, you only have 120 feet of this base material. And the goal, because you are a responsible and good cat owner, you want to give Houdini the maximum available space. So we have our sketch, and I'm going to label variables. I'm just going to call this guy X and this guy Y. Seems reasonable. Next, I'm going to write an equation for what you are trying to maximize or minimize. Remember, we're trying to get a maximum area, so my area is X times Y. And looking at this, it's like, oh, wait a second. We have too many variables here. This isn't a related rates question. So we're going to use other information in order to get rid of something. The other information we have is the fact that you have 120 feet of this base material. So if this whole thing adds to those red lines add up to 120, and knowing that's an X on the bottom, that means that Y is equal to, well, we have X plus Y equals 120. Let's go over here. So Y is 120 minus 2X. And if I chuck that guy in, I get A equals X times 120 minus 2X. Okay, next, we need to specify the domain. So what are the X values that we can use here? Well, the smallest the X could be, I'm not saying this would be a good pen at all or a good catio, but the minimum obviously would be 0. X has to be at least that. That would be a terrible one. The other way would be is if you had X as big as possible, which would mean like Y is as small as possible. So it'd be like this out and back, really skinny, infinitely skinny, like all the way skinny sort of pen. Again, not a good catio, but we're just setting our domain. But that would mean a maximum of 60. This is going to come back in a little bit. So step 1, make a sketch. Step 2, write an equation. Step 3, get rid of a variable as needed and specify the domain. Step 4 is going to be to find where the derivative is 0. So before I deriving this thing, I'm going to distribute because I prefer to avoid a product rule. So 120x minus 2x squared. So A prime is 120 minus 4x. And because I'm going to need it anyway in a moment, I'm going to go ahead and find my second derivative. So our second derivative, negative 4. So if we're finding where our derivative is 0, set my derivative to 0 and solve for x. So x would be 30. And we want to show that, yes, for sure, this is a maximum by looking at our second derivative. Since we have a second derivative of negative 4, A is concave down. And so if you have a flat spot and a derivative, we know we have a maximum. And then comparing to our endpoints of 0 and 60, the areas would be 0 for either of those. So obviously that is kind of clear. Let's compare this to our graph or look at our graph. So I have my equation into my y equals. Setting the window, this is actually where that domain's going to come in handy. If I look at my table and I put the 0 and the 60 and I get 0 on both of those, and I just put halfway between the 30 to get 1800. So to set my window, I can make my window go 0 to 60, or the negative one I think was already there. And my max, I went all the way to 2000, just so I can compare things. By the way, we can get our calculator to tell us the maximum if I go second trace, and then number 4 is maximum. Obviously minimum works too. And it asks me for a left bound. I need to just be physically to the left, like that. And I can hit enter. And then I need to be physically to the right. I can either type in a number or I can hit my arrow key and get myself to the right of the maximum, hit enter, and then enter once more. And it tells me, now this says 29.999999. Is that clearly 30? Yeah, that really is. So we do have a maximum. We know from our, from doing our calculus, but we also have it on a graph, which is really good that it works for both. The last thing is to answer the question in words. So the largest catio is 30 by 60 feet for a maximum area of 1,800, because 60 by 30. And we can get that 60, remember, by plugging in the 30 we had here. Square feet. And if your sentence is ambiguous, like, is this 30 by 60, like, which way is it? You could always say, like, as shown in the diagram, or you could say something like, the 60-foot section is parallel to the house, something to make it clear. So then here is that domain thing again. Okay, so now I added a little bit to this. How does your answer change if you can only go 25 feet away from the house? So if our domain was stuck with 0 to 25, that would definitely change our answer. In fact, if we went 0 to 25, our maximum area would be down to 1750. We couldn't go all the way to that 30. So that's what I mean by looking at the domain, because sometimes the situation in the genuine, fake, real life examples might force your hand a little bit. So that is a max-min problem.